good morning. Welcome you all to this NPTEL course on electrical distribution system analysis. And last class, we have seen the basic design and operation of distribution systems, and probably today we'll continue the same concept further. Now, one of the important aspects of distribution system design is voltage control. All equipment connected to the power utility system is designed for a specific voltage range, that is maximum and minimum voltage values at the consumer end are prescribed in the Indian Electricity Rules 1956. Now, let us say if you are not able to maintain the voltage between the specified voltage maximum minimum range, then what are the challenges? What are the impact of voltage drop? Now, voltage drop in the system affects consumers farthest from the substation who receive the lowest voltage, because consumers may be very far away from the substation, may experience a low voltage drop. Now, voltage on a primary distribution feeder varies from maximum at the first distribution transformer near the substation to a minimum at the last consumer on the last transformer. Now, hence, despite voltage variation, it is necessary to provide almost the same service voltage to all consumers. Based on physics, if you are connected very far away from the substation, you are expected to experience a low voltage, but nevertheless, as a distribution system designer, my main objective is to make sure all the customer get a reasonable range of voltage within its specified limits. Now, what are the cost implications of voltage range? Now, broad voltage limits increase the cost of equipments, especially sensitive devices like computers, and narrow voltage limits increase the cost of providing power within these restricted limits. Now, voltage drop and line losses are very well connected. Both voltage drop and losses depends on line impedance and loading. Lower line voltage drop and losses are desirable, often achieved by using larger conductor sizes. Now, use of conductors above a certain size yields diminishing returns in terms of reducing voltage drop and losses. Now, when you talk about impedance of a conductor, that is Z, which is R plus Jx, reduction is limited, particularly when the resistance is already very small and the reactance X reduction depends on conductor spacing but not the size. Now, optimum conductor size is necessary for any given loading in a distribution system. Now, if you see the voltage issue here, let us concentrate on a substation. Now, the consumers are connected at different distances from the substation. This is my consumer 1, consumer 2, consumer 3. What we are saying, the consumer 3, which is the farthest compared to the nearest consumer, which is at 1, will experience different voltages. But that voltage drop should be within a prescribed as well as reasonable limit. Now, as per ANSI voltage profile, let us not focus on 126, it could be 230, it could be anything, but this is your 1.0 per unit. And when you move distance, probably you can experience different voltages. Now, you could see that this point to this point and these two do experience a huge voltage differences, which is slightly interesting. So, the objective is to minimize the gap between these two voltage drops. Now, voltage regulation, as we learned from our undergraduate itself, is a very important concept, and we will try to understand what is regulation. System voltage regulation involves maintaining stable voltage levels at consumer terminals with fluctuations within acceptable and permissible limits. Since not all the loads reach a maximum at precisely the same time, it is necessary to modify these values by applying a coincidence factor defined as coincidence factor which is inverse of my diversity factor. So, CF is 1 upon DF. Now, how do you calculate regulation for individual loads? Regulation values for individual loads with various power factor may be obtained by using the regulation formula, percentage of regulation, sending end voltage, the difference between sending end voltage and receiving end voltage upon the receiving end voltage multiplied by 100 will give you the regulation. Now, there is one open question to all of you. Please try to answer whether to prepare a minimum regulation or a maximum regulation, which is good for the distribution system. Think of, we'll come back after some time. Main consideration for voltage regulation: avoidance of serious voltage fluctuation or flicker, maintenance of voltage close to an optimum level, limiting the voltage spread within established boundaries. Voltage fluctuation or flicker issues are usually linked to abnormal loads on power systems. Technical solution exists for these issues, but economic considerations can make them cost prohibitive if levels are set incorrectly or limits are too narrow. The practical approach is to provide the majority of consumers with an acceptable supply most of the time and improve the situation for less fortunate consumers as resources. The primary task is to investigate and decide on measures to optimize system voltage to consumers, ensuring distribution voltage remain within acceptable limit. Now, what are the regulatory standards for voltage limits? Different standards do define different values and ranges. IS 5613 and CA regulation prescribes plus or minus 6 voltage for LT and plus 6% minus 9% for HT supply to consumers. And for extra high tension voltage lines, that is 66 kV and above, the limits are between minus 12.5% to plus 10%. Means for high voltage network, the variation, bit large variations are acceptable. However, for low distribution lines or systems, maximum plus or minus 6% is acceptable. Now, depending upon the different geographical regions, even within India, different states do define different voltage variations, acceptable ranges. So, there do exist an inconsistency in voltage variations acceptable to different geography of the nation. For example, if you look at Madhya Pradesh, Maharashtra and Delhi, the ranges are given at different percentages. It is observed that there are differences in approach towards the voltage unbalance amongst the selected states. Some states do not specify any standard for voltage unbalance, and there are differences among the states who specify the standards for voltage unbalance, and hence we need to have a common standard and common voltage unbalance range acceptable across the system and across the country. Probably that would help for a larger extent. Now, moving to a very important aspects of harmonics. Now, the increasing use of nonlinear devices has escalated concerns over harmonic distortion in voltage waveforms. Devices like rectifiers, inverters, variable speed drives, furnaces, fluorescent lamps, TVs, UPS, computers and saturable reactors are the major sources of harmonic currents. Harmonics are primarily due to device having varying impedance in each half cycle of applied EMF or generating a non-sinusoidal back EMF. Impact on voltage waveform, that is, it's essential to access how harmonic currents distort the voltage waveform throughout an electrical network. Electronic loads drawing current at voltage waveform peak lead to inherent current distortion, potentially affecting the voltage. As per the IS 325/1996, the harmonic distortion in supply voltage up to 11 kV is limited to a maximum of 5% at any given point of time. Complying with standards like IS 325/1996 is crucial for maintaining power quality and reliability in electrical networks. Continual evaluation and analysis of harmonic distortion are necessary for effective power system management and to mitigate potential issues. Now, if you concentrate, a fully controlled thyristor circuit connected across load is responsible for injecting harmonics in my distribution network. Now, when I talk about a DC output, and you could very clearly see experience harmonics because of power electronics devices connected across the load points. If you see the order of harmonics, harmonic current content if alpha equal to 0 for each first, fifth, seventh, 11th and 13th. So the order of harmonics, as you could see, from varying from 8% to 100%. Now the harmonic calculation is very simple. Any periodic waveform of non-sinusoidal form can be synthesized by expressing it as the sum of the series of harmonics of the fundamental frequency using Fourier analysis. We know very well A0 is the average of the function over a period, also known as DC component. A and Bn are the Fourier coefficients for the nth harmonic and are calculated using the following integral over one period of the function. Now, when you talk about nonlinear load, it has been told that nonlinear loads are responsible for injecting harmonics. Nonlinear loads draw non-sinusoidal currents, leading to voltage waveform distortion or disturbances, not just within the local equipment, but throughout the power supply network, affecting transformers, lines, circuit breakers, and motors. As nonlinear loads become more prevalent in distribution systems, their effects need to be mitigated. Harmonics generated by these loads can flow through and potentially transmit from one consumer system to another. Harmonic frequencies are quantified as a percentage of the fundamental frequency component. Different situations affected by harmonics may require diverse characterization methods. The crest factor is one metric that measures a type of distortion. Distortions are majorly seen in case of loads. Those are connected with nonlinearity as well as power electronic devices. Only the fundamental wave of current contributes to energy transportation to the load. Harmonic currents are considered undesirable as they do not transport energy and effectively lower the power factor, acting as if the load itself is generating them. Now, the harmonic content K and the fundamental frequency content G are analyzed using the ratio of fundamental frequency current I1 to the total AC line current IL. It is assumed that the system's reactive inductance at harmonic frequencies is n times the fundamental frequency value, and the capacitive reactance is 1 upon n times with resistance remaining constant. Now, the international standard for power quality, that is IEEE 519/1992/2014 as well as EN 50160, talks about different harmonic standards. As you could see, IEEE 519/1992 specifies voltage and current harmonics limit up to 161 kV. Updated IEEE 519 recommends multiplier for current harmonics to reduce lower order harmonics. Most of the states adopted IEEE 519/1992 as their prescribed limit. Whereas EN 50160 talks about specified standards for voltage variation, flicker, unbalance, harmonics, voltage and main signaling voltages. Now, as per IEEE 519, we can see the voltage distortion limit. Now, the bus voltages are specified, individual voltage distortions are specified, individual voltage distortion as per 2014 is specified, and then we can calculate the acceptable TSD in 1992 as well as 2014. So, over a period of time, the TSD range has been slightly upgraded, which was especially for 1.0 kV and lower, it was not defined, but now you could see this is 8%, which is acceptable. So varying from 1.5 to 8% TSD at different voltage levels are acceptable. Similarly, we can see the current distortion limits for system rated 120 volt through 69 kV by IEEE 519. No changes. Current distortion limit for system rated 69 kV through 161 kV by IEEE 519, 1992, 2014, no changes. And similarly, current distortion limit for system rated from 161 kV above, both 1992 and 2014 are specified. Now, what are the recommendations for increasing current limit to reduce lower order harmonics by IEEE 519? That means the harmonic order limited to 25% of value given below, that is 5th and 7th, 1.4 times, 5th, 7th, 11th, 13, 1.7 times, 5th, 7th, 11th, 13, 17, 19, 2 times, and 5th, 7th, 11th, 13, 17, 19, 23, 25th is 2.2 times. Again, there is a huge inconsistency in our harmonics. If you concentrate on different states like Tamil Nadu, Gujarat, Maharashtra, Delhi, Madhya Pradesh, Andhra Pradesh, Karnataka, as we have discussed that the voltage variation within different states, acceptable voltage limits are different, and similarly, the acceptable harmonic percentage limit is also different compared to different geographic ranges. So, as per the CA regulation, as you could see, the TSD 5% with single harmonic content not exceeding 3% for 33 to 132 kV, and TSD 2.5% with single harmonic content not exceeding 2% for 220 kV, TSD 2% with single harmonic content not exceeding 1.5% for 400 kV, and similarly 1% for 765 kV. So, as the voltage increases, probably you can see the acceptable ranges keep on reducing. But to me, it is important or high time to have consistency in harmonic acceptability within different distribution systems of the state as well as the nation. Now, suggested approach to improve power quality and distribution of electricity, that is regulatory intervention. So, what the regulatory framework can do for betterment of power quality of any distribution system. We need to have KPIs for DISCOM's performances, bringing consistency in standards, monitoring framework, that is methodology and frequency, PQ monitoring system of substation levels. Though there is provision for penalizing the utilities for not adhering to the voltage variations and harmonics limits, majority of the consumers are not using the provisions for following reasons. First, absence of awareness among the end users, very low penalty or compensation by utilities to consumers, and absence of measurement and monitoring systems at user end to track the deviations and abnormal events. Majorly, the industrial consumers at 11 kV and above are responsible for huge harmonic injections. Probably those steel industries and welding industries, furnace industries need to be addressed at different level of regulatory commission to make sure that this harmonic or the power quality of the system can be improved by reducing harmonic injection by those industries. Distribution utilities need to design and implement awareness programs for the consumers by engaging with them periodically through structured awareness program. Voltage fluctuation is mainly due to load variation also. Load changes in an electrical network cause voltage drops along the line, leading the voltage fluctuations for other consumers. Frequent fluctuations can be annoying and disruptive to both consumers and sensitive devices. Devices such as computers and their power supplies as well as continuous process plants can be adversely affected by voltage fluctuations, potentially leading to operational disruptions or inadherent triggering of undervoltage relays. We also can measure the flicker using the following formula. Incandescent light bulbs are very sensitive to voltage variations, making changes in system voltage noticeably apparent as flicker. Tolerance to flicker varies with the frequency of voltage fluctuations. The voltage drop during the startup of induction motor is an important consideration in power system. The voltage drop experienced due to the starting current of an induction motor is influenced by the size of the motor, the power factor when starting, the impedance of the system, and finally the method of starting of the motor. For a three-phase motor, the voltage drop can be extrapolated from the equivalent single-phase case using the following expression. The percentage voltage drop also can be determined using the following equation. The power factor of the motor on starting is typically around 0.3, and the starting current for a direct online motor is between 4 to 7 times the rated full load current, which is huge if not specified. A factor of 6 is commonly used. The starting current of the motors can be reduced by using starting equipment such as auto transformer starting or star delta starting. Now, what are the methods to reduce flickering? Upgrading the power supply transformer to a higher capacity can help observe the fluctuations caused by a variable load, thereby reducing flicker. As illustrated in the following figure, using separate low tension LT feeders for general loads and welding set loads can segregate the steady and varying load consumers. This separation helps in minimizing the interference of the fluctuating welding loads, as I mentioned earlier, with other loads which could cause flicker. Enhancing the equivalent three-phase short circuit capacity of the system, which can be achieved by inserting series capacitors, helping in maintaining voltage stability during transient conditions caused by fluctuating loads. Now, at the load side countermeasures, inserting a series reactor in the circuit with the variable load can reduce the absolute value of the current variations, which in turn minimizes voltage fluctuations and flickers. Now, shunt capacitor and controlled by thyristor, though it is an expensive mechanism, the installation of thyristor controlled shunt capacitors can provide dynamic power factor corrections, responding quickly to changing loads and thereby mitigating flickers. Now, inserting a series reactor can also act to suppress overcurrent conditions, which can be contributing factor to voltage dips and flickers. These countermeasures are essential for ensuring that the power quality is maintained, especially in industrial settings where variable loads are common. They are crucial for avoiding disruptions in sensitive equipments. Now, there is one important factor known as ferroresonance. Ferroresonance can manifest in multiple forms within an electrical system, and these include stable subresonance at the fundamental frequency. Stable ferroresonance at the fundamental frequency, stable subharmonic frequency oscillation, continuous yet unstable self-excited oscillations, and transient oscillation that revert to subresonance. Now, this is the dangerous state in electrical network where the most potentially hazardous state in the fundamental frequency stable ferroresonance. This can cause voltage in the system to be significantly higher than the applied voltage, leading to the overvoltage that can be harmful to majority of the system components. Now, how this ferroresonant circuit, how do we form that circuit? The ferroresonant circuit in question arises from single phase switching of an unloaded or lightly loaded delta connected distribution transformers coupled with a length of cable. The cable's inherent capacitance, especially when underground, greatly increase the likelihood of ferroresonance overvoltage due to its higher capacitance per unit length compared to overhead lines. Now, prevalence of overvoltages due to ferroresonant overvoltage typically range between 1.5 to 2 times the per unit value of the normal voltage. The entire cable length, transformer binding, cable termination, and the open phase of the switchgear can be subjected to these overvoltages. Now, how do we avoid ferroresonance? To prevent ferroresonant conditions, it is recommended to energize the cable first, followed by the transformer, and to de-energize in the reverse order, transformer first and then the cable. This avoids the simultaneous single phase switching of transformer and cable, which is primary conditions for ferroresonance. The following circuit represent the single line diagram of ferroresonance circuit arrangements through which the ferroresonance can be avoided. Now, moving into the system losses, especially distribution losses, includes no load losses, that is transformer magnetizing current, load losses, that is so called I square R losses, reactive losses from poor power factor, regulation losses due to voltage drop, and non-technical or commercial losses like or elite connections and metering issues. Loss measurement and analysis, on-site feeder measurements and load flow studies determine the total technical losses, commercial losses, and found by subtracting these from the total losses, encompassing theft, unaccounted power, unauthorized use, and metering and billing deficiencies. So, this is probably unaccounted as well as commercial losses together. High loss feeders are targeted for further investigation and loss reduction measures, such as installing energy meters for audit purposes, using aerial bunched cables, and converting low tension lines to high tension lines. Losses vary by state due to different system characteristics, design adequacy, maintenance quality, and the efficiency of electrical joints. Use of efficient transformers and technology is recommended majorly for loss reduction. Now, what are the benchmarking and comparison? Utilities should be compared with consideration of their unique attributes and consumer mix. Losses significantly vary internationally, with some countries achieving much lower system losses through strategies like locating generator closer to the load centers. And the system losses, if you see, starting from generation step of transformer substations, which is close to 11.58%, transmission and sub-transmission lines 20%, sub-transmission grid substations 12%, primary feeder and line equipment 25%, distribution transformers 17.22%, secondary and service line and grounds are 11%, and meters are close to 0.6%. This is how the total losses are distributed. Now, these are the source of losses, and this is the aggregate technical and commercial losses in the power sector state-wise and AT&T loss. As you could see, it varies from actually as minimum as 10% to as maximum as 25%. Now, to conclude, distribution losses, especially in India, become an issue. Considering the peak energy deficit and energy shortage, any reduction in distribution losses will indirectly add generation to my system, and hence we must focus how the system losses can be reduced. With this note, thank you very much.